Hello class, this is Tom Austin. I'm here to do a presentation on my social networking and what I did with that. So let's go ahead and get started. First I'm going to talk a little bit about open flights, which is what I used, about how I process the data to get it into gephi. Also about analyzing the open flights data, and then any questions that you might have. The data is available at the Open Flights website. I've got a link here on the slide. It's in a text CSV file format. The airport's DAT file contains the node information. The routes DAT file contains the flight information. It contains information about airport nodes, flights from all over the world, 6,977 airports, 68,820 flights. The nodes represent the airports. The node labels, in the case that I used, are FAA codes. The edges are directed. You fly from somewhere to somewhere, and they are weighted depending on the number of flights. And that happened on the way into gephi. Alright, so as you can see, this is where the nodes are located all over the world. Some areas they're more concentrated than others. And as you look at the flights, tons of flights all over the place. Some nodes don't have much activity, if any, commercial anyway, that's in this database. So I went ahead and imported the files into Access and made some queries to eliminate unneeded columns, because there were a lot of columns in the two CSV files. So then I exported the queries basically to CSV files, renamed the columns so I could get them into gephi, and I did the import. The import went fine. I was able to display them, but then once I ran when I analyzed the statistics, the force layout had problems reprocessing and visualizing. So I had to do something about that. So I rewrote the queries, and I only included nodes from US and Canada, and only included edges from US and Canada. So the new data set had 1,743 nodes, 11,691 edges. This time, when I ran the statistics and I did the computations, the layout worked, so I could better visualize the nodes. I also then filtered the nodes to greater than 1 degree. I figured they better at least have one flight. So now there's 429 nodes instead of the 1,743. Rough measures of the network after all this processing: 429 nodes, density 0.002, out degree 5807, in degree 5803, fairly well balanced. Total degree was 11,610, the addition of those two. Diameter 13, average length 3.8. And the geodesic distance, 648,008. So here's just sort of a picture of how it looks with the nodes grouped and by color, and they were sized by degree. We'll go through this in a little bit more detail. Alright, let's see what our degree distribution was. So I pulled this data into Excel and took a look at it, and it looks like it's a power law distribution. We have a very large number of nodes with a small degree, and as you move out along the horizontal axis, you can see the degrees go up, but the number very quickly reaches close to 0. So definitely there's a lot of power and very few airports, as I should say. There's a lot of flights that go out of very few airports, and a lot of the airports don't really have many flights going in or out of them. What were the top 10 airports by degree? Well, Denver, Chicago O'Hare, Atlanta, Dallas Fort Worth. We got down at the bottom here, number 10, we have LAX. And they go from 339 degrees down to 205 at LAX. If we take a look at this same information, the nodes here are shaded by size and degree. Similar, Denver, Chicago O'Hare, Atlanta, Dallas Fort Worth. We see LAX is still in there, but it's a little bit smaller. I was a little surprised to see Denver had more flights in and out than any other airport in the U.S. I did look at in degree and out degree. Didn't seem to change the ranking, so didn't use that. Something interesting to note: the passengers, the largest number of passengers, don't really match up to these degrees here. So the number of flights isn't necessarily the number of people that fly in and out of the airport. We can take a look at another measure. We can take a look at top 10 airports by page rank. Number of in and out degrees, and we see here it doesn't seem to change that much. You know, Denver, Chicago O'Hare, Atlanta, Dallas Fort Worth. And down on the bottom, LAX has changed places with, I believe that's Charleston. So some changes, but not much, and it may be because the in and out degrees are fairly well balanced. If we take a look at the page rank here, you know, we have similarities to the sizing and color by degree. The nodes aren't exactly the same size, but they're close. Again, I think it's because the network is fairly symmetric. Most of the nodes, if they have incoming flights, they have outgoing flights, about the same number. Alright, well, what about eigenvector, or eigenvalue, the influence? So it shows some movement in the top 10 nodes. A lot of them are still the same top 10. We have LAX dropped off. But, you know, we've got Denver, Atlanta, Chicago O'Hare, Dallas Fort Worth. Most of them stayed in the top 10. So a little bit of movement, not a lot. So if we take a look at this chart, which shows a visual of these nodes, you can see they appear to be a little bit more equal in size. Again, I don't know whether that's gephi or just the way we had it sized the nodes. How about closeness centrality? You know, which of these have the shortest distance to the other nodes? Something I thought was interesting was that some of the larger airports, we got Denver in there, Chicago O'Hare, MSP, I can't remember what that one is, but they were in the bottom 10. Really high degree nodes, but not the closest to the other nodes in the system. Some of the top 10, the ones with the Y's in, are from Canada, so that was kind of interesting, that a lot of the ones in Canada have a higher closeness centrality than the ones in the U.S. I don't believe, you know, they aren't the highest by degree or any of the other measures we've used, but it's interesting to note that they have a shorter distance to the other nodes. Alright, if we look at this picture here, we've got the degree by color still, but the closeness is by size. And again, it looks like a lot of the lower degree nodes are closer to the other nodes than the higher degree ones. I don't know why that is, but that's the results that we had seen, or I had seen. Sorry about that. What about airports by betweenness? Airports you need to that act as a bridge to go on somewhere else. That connect and group other nodes. We see Anchorage is pretty high on the list. Chicago O'Hare is pretty high. Denver is pretty high. Seattle is pretty high. So some of the same ones that were in the top 10 are here, but Anchorage certainly wasn't in the top 10, but it definitely ranks the highest by betweenness value. So that's interesting that to get somewhere to one of the shortest paths to get somewhere else might be through Anchorage. Okay, so if we take a look at this, we're showing betweenness here by size and the darker colors by degree. And there again you see Anchorage larger than any of the others. But you got some of the higher degree nodes that are still fairly large: Denver, Atlanta, Chicago O'Hare, Dallas-Fort Worth. But it's interesting. Seattle and Anchorage, they're not the highest degree, but they do have a high betweenness value. Alright, here I used modularity to find the communities. We can see about 4 or 5 in this chart as we're zoomed way out. How many are there really is what I thought when I looked at this, because I can only see it looks like 5 or 6. But if we take a look at this, I made a pie chart that could show us the different communities by the number of nodes. And you can see, there's 5 or 6 that are pretty large. 1, 2, well, maybe even 7 or 8 if you go down to the 4 or 3%. But if you keep the bigger ones here, you got 1, 2, 3, 4 pretty large, and then you got a few at 5 and 4. There's quite a few there, however. There's probably 12 or 13 groups that are very, very small, and that's why we did not see them on the chart that shows us the nodes. Okay, so I zoomed up a little bit, and I didn't do all the pictures here, but this shows us, there's a lot of dense connections between the green nodes. So the green group corresponds to the largest percentage of nodes in the previous slide, and we can see the dense connections between the green nodes and the fewer connections to the other colored nodes there. We could have zoomed in on some of these other groups and taken a look at them, but running out of time here, so I'm done with my presentation, and I'd be happy to try and answer any questions you might have. Thanks for listening.